Thank you for that nice introduction. I appreciate it. First of all, I just want to let's give one more round of applause for our keynote speakers, early selected talks, and our rec scholars. I mean, fantastic way to start the day. But I guess I'll get started because we got a lot to get through. But the title for my talk is Novel Tau Antibodies as a Diagnostic and Therapeutic in Alzheimer's Disease. So a little bit of background before we begin, just because we're getting back into the basic research, preclinical stuff. So AD is due to the pathogenic accumulation of two proteins, tau and amyloid beta. So tau normally resides on microtubules, but over the course of aging, it falls off these microtubules, sending it towards a cascade, towards aggregation, and the generation of the hallmark phenotype of AD tau tangles, or neurofibrillary tau tangles. Now, this all occurs intracellularly, and extracellularly, we see an accumulation of amyloid beta plaques. Now, it's important to note, particularly for this talk, that both amyloid beta and tau are necessary for genuine Alzheimer's disease. You cannot have AD with just one of these proteins. Both need to be present to actually have the diagnosis of AD. Now, us in Todd's lab, the Tau Meister, as you might imagine, we're more interested in tau than amyloid beta, but we are interested in both proteins. Now, tau, as you can see by this figure, is highly decorated by post-translational modifications, or PTMs. Now, classically, phosphorylated tau has been the most well-studied post-PTM of tau. However, we in Todd's lab are more interested in a far less studied PTM known as tau acetylation. And as I hope you can appreciate from this figure is that the vast majority of the acetylation residues reside within the MTBR or the MTBD. So this is actually the region of tau that binds microtubules. Now, recently, some really, really beautiful cryo-EM work has actually unraveled the structure of tau aggregates. And so if you look here at the core, you'll see basically stacks of tau proteins on top of one another, followed by this jellyfish kind of looking coat to the left. If you zoom in a little bit further and look either from top down or bottom down, you actually see two, let me get my laser here, two interfacing tau molecules. Oops. Can you guys see that? Oh, doesn't work. Okay. Two interfacing tau molecules in kind of like this candy cane conformation. And if you zoom in one layer more deep, what you'll find is that each of these candy canes is robustly covered with acetylation residues, which are labeled here in blue, far more than phosphorylated tau residues. And to kind of bring this all together, this whole candy cane is basically comprised of the MTBR, this very important region of the tau protein. And the authors of these cryo-EM papers have stated that basically the core of these tau aggregates is highly enriched with acylated tau, and they think that this acylated tau actually stabilizes the core of these tau aggregates. So before I joined the lab, the Tau Meister, Todd, had actually found two particularly pathogenic acetylated residues on tau, those being ACK280 and ACK311. Using previously made rabbit polyclonal antibodies, Todd was able to find out that not only are these two acetylated residues found in postmortem AD brain, but they co-localize with markers such as PHF1 and thioflavin S. Now, what's kind of more interesting and what really kind of set us on this course is that both phospho-tau and acetylated tau do correlate with AD. They track with AD. However, if you look in control patient brains, often you will find some level of phosphorylated tau. However, under no circumstance have we ever detected acetylated tau in a control patient, which suggests that AC tau might actually be a better disease marker for AD than phosphorylated tau. It might be a bigger driver of the disease and potentially a better therapeutic and potentially a better biomarker. So moving forward, as I had mentioned, Todd had already generated polyclonal rabbit antibodies against these two residues, but we wanted to generate monoclonal mouse antibodies against these two residues. One of these reasons being is that these monoclonal antibodies are continuously renewable, and two is that they're more commonly used as therapeutics, particularly in immunotherapies. And so as you can see here, we kind of whittled down a total list of clones from like 3,000 down to like 40. Those were handed off to me. And then from that 40, I picked basically our best ACK280 clone, 19B6, and our best ACK311 clone, 15E8. We validated and showed that these are highly specific by Western blot, by immunocytochemistry and primary neurons. Furthermore, we could actually probe post-mortem AD brain, and we found that both these antibodies detect a great deal of tau pathology in these patients' brains and cortex. If you zoom in a little bit further, you find that these antibodies not only detect the hallmark neurofibrillary tangles, which you can see here, but right next to it, you see a diffuse neuritic plaque, very similar to what you'd see with an amyloid beta antibody. Just for the sake of time, I'll be very brief about this last panel, but essentially, as a proof of principle, we were able to deliver our antibodies to primary neurons expressing acylated tau and showed that these monoclonal antibodies engaged acylated tau, showing that indeed the antibodies do engage their appropriate target, which bodes well for its potential as a therapy. Obviously, we love this. We love to see this. We have 2 brand new tools that we have already begun sharing with various labs that can detect really, really pathogenic sites on tau. All right, but moving on to the second half of this talk, can we actually functionally use these AC-tau antibodies as a therapy for Alzheimer's disease? So many of you are familiar. There are currently 2 FDA-approved drugs for Alzheimer's disease. Both are immunotherapies targeting amyloid beta, Leqembi and Kisunla. However, the recent FDA approval of these drugs has actually spurred a lot of interest in the tau field to try to attack and target tau via these immunotherapies. And as you can see here, this is a tau protein and all its domains, followed by underneath are all the current tau immunotherapies in clinical trials. What I hope you can see here is that all of these immunotherapies are targeting phospho-tau residues. And second of all, I want you to note that the MTBR is completely vacated. There are no immunotherapies targeting this region. Thus, our antibodies could potentially be not only the very first acylated tau immunotherapies, but the very first MTBR targeting immunotherapies. And so I actually have a really great figure that kind of shows how these immunotherapies work. They actually get into the brain and mop up pathological species of tau. So let me just see if I can find it here. Yeah, there it is. So if you look here, these are our antibodies, and down here, labeled in blue, are our acylated tau, demonstrated so well by the Todd Meister over there. I don't get that many opportunities to take a picture of my boss doing manual labor, so I had to take advantage. He does fine me pay every time I show his picture, so this cost me about $500. But moving forward, so we wanted to pursue a preclinical assessment of our antibodies in an AD mouse model. However, I'd mentioned that both amyloid beta and tau are necessary for genuine Alzheimer's disease. So we wanted to use a mouse model that contained both that bullet and the trigger. And how we did this, we actually crossed the PS19 tau mouse model to the 5xFAD amyloid beta mouse model. And as you can see here, by 10 months of age, they accrue a great deal of acylated tau in the hippocampus and cortex. And additionally, as you can see labeled here in orange, they develop a great deal of amyloid beta plaques as well. So what we did is we actually injected these mice 10 mg per kg with 19B6, or ACK280 clone. We did weekly IP injections from months 3 to 6 months of age, followed by a full behavioral battery from roughly 6 to 9 months of age. Now, these mice, typically, we see about 50% mortality by 10 months. But again, this cross-mouse model is really a great way to kind of mimic symptomatic AD, containing both that bullet and the trigger. And our hopes by using this model is that we have a greater chance of translating this to the clinic. All right, so kind of the gold standard for assessing cognitive function in mice is known as the Morris-Water maze. And essentially how this works is that a mouse is dropped into a big vat of water with a singular hidden platform. On day 1, it takes a while for this mouse to figure out, hey, this platform's in the bottom left. But over subsequent days of training, it finds where this platform is and it can reach it faster. However, if you have a cognitively challenged mouse or an AD mouse, it can't learn this task as well. And we can actually take this one step further. So we can actually, after that initial hidden maze, we can actually move the quadrant to the opposite side, which is kind of mean, but it is a more sensitive test because what you're requiring the mouse to do is relearn that task. And it's a measure of cognitive flexibility and really kind of a more sensitive measurement of cognitive defects. So during this first phase of the water maze, we found, again, we used just wild-type, completely wild-type C57 mice as a cognitively healthy baseline. And as you can see, these mice learn this task quite well over the course of 9 days. When we looked at our AD mice, either PBS injected or ACK280 injected, we actually found that all three conditions basically track together. So all three sets of mice seem to learn this task pretty much equally. What was interesting is that when we looked at the Morris-Water maze reversal, we saw a really robust phenotype. So these wild-type mice, just like in the hidden maze, they found over the course of 9 days, they found this platform was very well. But these PBS-injected AD mice basically plateaued after day 2. They were unable to learn where this reversal hidden platform was put. What was more interesting is that when we treated these AD mice with our ACK280 antibody, these mice actually tracked really, really closely with completely wild-type mice. And in fact, these ACK280 mice were actually not significantly different from wild-type mice by this task. Now, this is a limited number, so this is just 4 to 7 mice per condition, but by the end of October, we'll have effectively quadrupled our number of mice, and so we'll basically look at all the behavior data, section the brains, and stain for tau pathology, including plaques and also acidylated tau. But currently, we are cautiously optimistic that we might potentially be approaching a new therapy for AD. And just briefly, just because I teased using these antibodies as a diagnostic, we indeed, because we think AC-tau is more specific for AD than phosphorylated tau, we think that this might actually serve as a really, really sensitive biomarker. And this work is currently driven by a wonderful undergrad in the lab, Avery Celine, who is maybe the most diligent, awesome undergrad I've ever had the experience of working with. If you see her, please tell her hi. She's awesome. And my wife, Dr. Bryan. However, we're not really experts in this, and I feel like every time I come to Slam Dunk, I'm not an expert in something, and I leave here with a new collaboration. And this Slam Dunk will be the exact same way. We've recruited Dr. Bin Zhu from NCCU with all his expertise in validating these biomarkers to our team, and hopefully next Slam Dunk we'll be reporting on a brand new AD biomarker. All right, with that, I just want to thank everybody, my lab. First of all, is incredible, including my mentor, Dr. Todd Cohen, even though I like to put his face on every one of my presentations. Additionally, my lab is incredible, but I do want to give a special shout out to my wife, Dr. Bryan, who usually just had to deal with my insanity at home, but then she joined Todd's lab, and now she has to deal with my insanity both at work and home. But luckily, we come home to this beautiful budding neuroscientist, Addison, every night, so that helps. All right, thank you guys, and I'll take any questions you guys have.
Wonderful talk, Miles. Congratulations on those super exciting data. I think those are textbook type of data. I have a quick question about the using acetylated tau. You find not only intracellularly, but also in the plaque. Is this unusual compared to the literature? How do you explain it?
Yeah, so we get this question often. So we have actually looked at some other tau antibodies, and we can somewhat see diffuse neuritic plaques. So like AT8, we've stained human brain. In fact, these exact same 3 patients with AT8, and we do somewhat see diffuse plaques. With these ACK280 antibodies, they do seem much brighter. And we don't think this is cross-reactivity with amyloid beta. What we think is happening is that there's basically neurites from dying neurons interwoven into these plaques, and that is actually the signal we're picking up in those diffuse plaques. It's not amyloid, it's basically AC-tau interwoven into amyloid beta plaques, which we think, and we have publications showing there's a great deal of relationship between amyloid beta and the induction of acylated tau. But good question, thank you. All right, thank you guys all for your time.